Hey guys, Mrs. Dance here. So we'll see how long this video turns out to be, but we're on lesson 8 and the objective is written down for you if you could just copy it. And still we're writing piecewise functions, but now it's about like word problems, real world situations. And you'll see that sometimes it's hard to see where the line hits the y-axis, and we know that that's really a very important thing to find in order to write that linear piece. So we're actually going to learn about shifting with linear pieces. If you understand the shifts with our absolute values, then you understand these shifts already. So in order to make it more clear, I'm actually going to go out of order. We're not going to do the do now first. So this is where you wrote your objective, and here's your do now. But I actually want to turn to page 47. And we're going to do number 3. So a tortoise challenges a hare to a 20-mile race. So I'm actually going to look at my graph already. I see that this is the distance from the starting line. So this 20 right there is where the race is going to end. I just want to have this in mind. The hare is so confident that he allows the tortoise to start with a 10-mile lead. So I guess the hare is going to start here at the starting line, but the tortoise is going to start with a 10-mile lead. The hare always runs at a speed of 10 miles per hour. So 10 miles per hour, this is my rate of change. So it's like we're going up 10 over 1. Be careful with what your scale looks like, though. Be careful when you're going up 10 over 1. So if we're talking about the hare starts at 0, and he goes 10 miles in 1 hour. But he stops for a 2-hour nap, which means this distance stays right where it was for 2 hours. So this is him going 10 miles an hour. He stops, takes a nap for 2 hours. And remember, it says that the hare always runs at a speed of 10 miles per hour. So after his 2-hour nap, after his 2-hour nap, he's going to continue 10 miles per hour. And now he made it to the finish line, because remember it was going to stop at 20 miles. It took the hare 4 hours to make it to the end. So I'm actually going to label this piecewise function h for hare, h of x. Now I want to graph the tortoise. Remember, the tortoise started at a 10-mile lead, and he goes 4 miles per hour. So be careful what your scale's going by. I think it's going by 2s. 2, 4, 6, 8, 10. Yes, so the y scale is going by 2. So if he goes 4 miles in an hour, that's where he is after the first hour. He made it 12 miles after the first hour. And he continues the whole way without taking a break. So 4 miles an hour and 4 miles an hour. Now I know I just crossed the finish line, but I needed to do this so that I could see where this line is going. So this point really isn't part of the function because he stops when he gets to the finish line. So I'm going to erase this. If he can go 4 miles in 1 hour, obviously he can go 2 miles in half an hour. That makes sense, right? So this is the tortoise. I'll call it T for tortoise, T of x, right? This is my x-axis. This is my y-axis, but I graphed the hare and I graphed the tortoise. And it asks who wins the race. Well, the tortoise made it there in 2.5 hours. The hare made it there in 4 hours. So the tortoise wins. So that's about graphing a piecewise function from a given situation. Now they're asking us to write equations for each animal. Really, they're asking us for the function. It's actually two different functions because there's a t of x and there's an h of x. So this is where we have to be careful. Let's do the tortoise first. He's so easy. He's only one piece. It's really not a piecewise function, I guess, but we'll say that t of x equals, remember he went 4 miles an hour, so we know his rate of change is 4. We used x as the time, and he started, remember, with a 10 mile per hour, a 10-mile lead. This exists from when x is 0 to when x is 2.5. I would say it's equal to in both spots. At 0 time, he really is here at 0 miles. At 0 time, he really is here at 10 miles. And at 2.5 time, he really is here at the 20-mile mark. So the hare is a bit trickier because it is a piecewise function. It's this last piece that makes it a little tricky. But I'm going to write something for h of x. I know there are 3 pieces. First piece, not so bad. He went 10 miles per hour. And his y-intercept is at 0. You don't have to put that plus 0, but I'm just going to put it just because. And that's between 0 and 1. I'll make it equal to in both spots. When he's taking his nap, it's a horizontal line at 10. And that exists from 1 to 3. I can't make it equal to the 1 here because I made it equal to in the top. I just said I can't make it equal to. The 3 I can make it equal to, or I could choose to make it equal to in the other one. I'll make it equal to here. And now this last piece is the trickiest piece. So what makes it tricky is trying to figure out where it's going to hit the y-axis. I think we can do it. If this piece continued, it would be right here at 2, 0. If it continued, it would be here, and this is like negative 10 on the y-axis. And if it continued, it would be here, which is negative 20. So I said it was tricky, but it's not so bad. You just have to be really careful. So he's going at a rate of 10 miles per hour, but this piece would have hit the y-axis at negative 20 if it continued. It doesn't continue. It really exists from 3 to 4. I can't make it equal to the 3 because I chose it to be equal to in this other piece, but he does finish. He is there. It does equal to the 4. And this was the piece that must have gotten erased if someone was given this piecewise function. But this is where I want to try and teach you about some shifts. So sometimes it's just too difficult to find where it's going to hit the y-axis. This one wasn't too difficult, but sometimes it is. I want to show you that you can use shifts. The shift works just like it does with the absolute value. So if I were to write this piece using a shift, we know that he's going 10 miles per hour, so we feel like writing 10x. But remember with our shifts that there's something inside the parentheses with the x, and then there's something outside. This inside is a shift right or left, and this outside is a shift up or down. If I choose this point, since it's part of that line, as my shifting point, from the origin, it shifted 3 units to the right. Remember, to the right, we say is the opposite sign, so it would be a -3. And it also shifted up 10 units. This should be mathematically equivalent to what we wrote over here. And the way that we could tell if it's mathematically equivalent is by simplifying this. What if I were to distribute? I get 10x minus 30 plus 10, and when I combine these like terms, I have 10x minus 20. This is mathematically equivalent to what I did over here. So this shift really works. And then some people say, well, how do you know what point to use for the shift? You know what? It doesn't matter what point you use. It always works. And we can prove it by even picking this point. So again, the rate of change is still 10, and we usually put an x next to it. But I'm going to use parentheses because I want to do my shift. So if I'm using this point as my shift, now I'm going to say it shifted 4 units to the right. So I'll put a -4. And if I'm using this point, it now shifted up 20. If I simplify this, I get 10x minus 40 plus 20, which guess what, is 10x minus 20. It is still the same thing. So what we just learned here was how to write a piece of an equation using shifts. You still find your rate of change like normal, but you put the x in the parentheses and you use a point for a right shift and use that same point for an up or down shift. So now we're going to go back to the do now. The do now was like too hard to do by trying to see where it hit the y-axis. So we have to do it using shifts. So I just wanted to teach you these shifts first. So now back to the do now. So we have a situation in which a wireless provider offers customers a monthly plan that costs $50, but then charges 40 cents per minute, so it's like a rate of change, for every minute over 1,000. And the graph below shows this. So it makes sense that if you pay just $50, makes sense that it's just a horizontal line. For all these minutes, it's $50. So you could talk for 250 minutes and you're paying $50. You could talk for 500 minutes, $50. 750 minutes, $50. Even 1,000 minutes, right? Because it's $50. But once you get over 1,000 minutes, that's when they start charging more. So over 1,000 minutes, that's why this line is increasing. They start charging more. So first question. So how much does it cost to talk 500 minutes? So we could see that on the graph. It costs $50. So they're asking, what's C of 50? What's C of 500? Oh, it's 50. How about 1,000 minutes? Still $50. So C of 1,000 is still equal to 50 because the slope is 0. It just constantly stays at 50. But now, how much does it cost to talk 1,250 minutes? So let's just see where this hits the graph, and let's see where that y value is. Let's be careful and see what our scale is going by. This is really 0. The 0 is kind of floating out there. It's going by tens, right? 10, 20, 30, 40, 50, 60, 70, 80. So it is going by tens. So if this is 120, 130, 140, 150, and it makes sense to get up to 160 there. So for 1,250 minutes, it's going to cost $150. What is the slope of the line between 0 and 1,000? Right here. Remember, horizontal lines have a 0 slope. And then it asks, what's the significance of this slope as it relates to the situation? Well, it stays at 50 because you're charged a flat fee of $50 for any number of minutes between 0 and 1,000. Sorry for that. So it shows that the cost remains $50 for 0 minutes to 1,000 minutes. It really shows that there is no change in that rate of change. Then it asks, what is the slope of the line after 1,000 minutes? So it's definitely changing here. So we can pick some nice points. I can pick that first point, and then the next one I could choose is this. Be careful, it's not up 2 over 1. Remember what we said our scale was going by. It's going by tens, right? So this is up 20. And now let's take a look at this scale. If that's 250 and this is 0, must be going by 50s, right? This is 50, 100, 150, 200, 250. So each box represents 50. So this goes up 20 and over 50. So the rate of change for this whole piece is 20 over 50, which if I actually divided that, I get 0.4, which makes a lot of sense to me because of what we said up here, 40 cents per minute. 0.4 is 40 cents. So that really makes complete sense. The slope of the line after 1,000 minutes is 0.4, or you could write 0.40. And the significance of this is that it shows the cost of 40 cents per minute. And then the last thing is the hardest, right? The piecewise linear equation. Just so that I can zoom in better, I'm going to be writing my equation up here so that I could show you some work and zoom in on my graph. So there's only 2 pieces. Oh, this is c of x's function. The first piece, easy, horizontal line, is at 50 from 0 to 1,000. We're actually going to make it equal to at 1,000 because of these words that it's 40 cents per minute for every minute over 1,000. So this 1,000 must be included in the first piece. The next one, rate of change, we already found, not so bad, but where does this thing hit my y-axis? I can't figure that out by extending it. It's just way too low, definitely in the negatives. So I want to use my shift. So it's a right shift, so I'm going to subtract something. I'm going to use this first point of that piece as my shift. I could look at the number right here. It shifted to the right 1,000. And it shifted up 50. kind of ran out of room for where it exists, so I'm going to put it down a little below. It exists for x greater than 1,000. I don't have to like distribute and simplify this. That's an acceptable equation. So since it's acceptable, I choose to leave it. I don't do extra work if I don't need to. If you really wanted to know where it hit that y-axis, we would distribute. And that's at negative 350. But again, this isn't necessary. And there we go. That's the piecewise function. This is really part F down below that I wrote here. So we're writing piecewise functions just like always, but if you can't really see where it hits the y-axis, then you use a shift.